In this section, we talk about the concept of the dot product. In previous sections, we talked about operations on vectors. We talked about how to add, subtract them, how to negate them, how to multiply them by a scalar. What we haven't seen is how to multiply a vector times another vector. It turns out that there's more than one way. The reason we have different types of multiplications is because they serve different purposes. The first one we're going to begin with is called the dot product, called so because the symbol that represents that multiplication is a dot. So, definition. Let U be a vector in two dimensions, U1, U2, and let V be a vector also in two dimensions, V1, V2. Then the dot product which is denoted as U dot V, hence the name dot product, is given by you multiply the first components together, U1 times V1. You multiply the second components together, U2 times V2, and then you add those results. If you have U is equal to a vector in three dimensions, U1, U2, U3, and V is a vector in three dimensions, V1, V2, and V3, then the dot product U dot V is given by, again, the component-wise multiplication all added together. U1 V1 plus U2 V2 plus U3 V3. If you had a vector in four dimensions, 5, 6, 7, 8, 9, 10, whatever, it all works the same way. If you have more components, you're simply adding another term to this sum. Note that you must have vectors in the same dimension in order to find the dot product. 2D dot 2D, 3D dot 3D. You wouldn't be able to take this times this. You'd have to have the same number of components. All right. So if we define multiplication this way, it's still maybe not clear why we want to multiply this way, but let's say that's our definition. Okay. Then there are several properties that come about from this definition. Theorem. And here we have properties of the dot product. All right. First of all, let's start off with a few vectors. Let's let U, V, and W be vectors in the plane. Notice the plane meaning two dimensions, the XY plane, okay? Or in space, meaning three dimensions, X, Y, and Z. All right, so here that's this situation, and this is this situation, plane or space. All right, so we have vectors in either space. Now notice this is one or the other. You can't mix them. They're either all in the plane or all in space. Okay? And let's have C be a scalar. Just a regular number. Then all the following things are true. If you take the dot product, it's commutative. So the product U dot V is equal to the product V dot U. Note that this is not something to be taken for granted. Not everything in mathematics has a commutative multiplication. For example, matrices. If we think back to algebra, when you multiply two matrices together, the order of multiplication matters. The product of the matrix M times the matrix P is not the same as the product of P times M. The order matters. But here, for the dot product, it does not matter. You have commutative multiplication. which is nice. You never have to worry about what order it's in. Not only do you have commutativity, but you also have one of our very favorite properties, and that's the distributive property. If you take this sum and multiply by this vector multiplies this first term plus this times this second term over here. So you have the distributive property. The distributive property. You also have, say you're multiplying two vectors together this way, and you multiply that result by a scalar. That's the same as if you were to first multiply together your scalar times your first vector, and then take the dot product with your second vector. And that can be brought over, and you can say, okay, that constant can be multiplied times the v instead of the u. And then you can take the dot product of those. And that's associativity. In other words, it doesn't matter how you associate these. Any pair can be multiplied first. This pair, or this pair. So that means that the dot product is exhibits commutativity, the distributive property, and the associative property. The next one, if you take the 0 vector and dot it with any old vector, doesn't matter which one, then you're going to get the number 0. The number 0. Don't you mean the vector 0? No. Notice right here when you take the dot product, you take this component's a number, and so is that one. So if you multiply them together, you just get a number. And same thing here, that's a number. And a number plus a number is a number. So the dot product of two vectors gives you a scalar. So right here, when you multiply together the 0 vector, 0, 0, and the vector v, v1, v2, you're going to get not the vector 0, but the number 0. Here, let's just write this to the side. Note, if you have a vector dot another vector, you don't get a vector, you get a scalar. In some older books, the dot product is also called the scalar product. But we really don't want to do that right now because we called this scalar multiplication. So calling one scalar multiplication and calling the other one the scalar product is a good way to confuse everyone, right? So we settle on this more distinctive name, the dot product. So a vector dot a vector is a scalar. It's just a number. And then property number 5 is if you multiply a vector times itself, v dot v, that's going to give you the magnitude of v quantity squared. All right, the proof of this. The proofs of all of these are pretty much the same. When I say they're the same, what I mean is they're proven the same way. Just like when you prove things about scalar multiplication, or when you prove things about addition or a subtraction of vectors, the general outline of the proof is you write everything in component form. You pick one side, usually the left. Write everything in component form, simplify, and then write it back in vector form, and it should give you what's on the right. Here, that's no different. If you just take one side, write it in component form, and simplify, it'll spit out the part on the right. So instead of proving all of them, I'll go ahead and prove one of them. I believe your textbook proves the very first one, so I'll go ahead and prove the second one. So proof of number 2. All right, so let's see. Let's take u dot the product of v plus w. All right. Here I'm going to go ahead and prove this in 2 dimensions in the plane. I'm not going to do it in space, although you'll note that in space it works the same way. All you would have is one more component. So if you can prove something for vectors in the plane, just adding another component is what it would look like for a proof in space. So here I'm going to do this in the plane, mostly because I don't want to write a third component. I'm going to save a little bit of ink here. All right, so this would be, well, let's see, my vector u is u1, u2, And then we're going to multiply that by v1 comma v2 plus w1 comma w2. Okay. Well, we know how to add vectors. That's just done component-wise. So that's going to be u1 comma u2 dotted with, if you multiply this, that's, if you add this, that's v1 plus w1. And that's v2 plus w2. That should be, there we go. All right, so we've gone ahead and added those. But now, we're going to go ahead and take the dot product. Here, we added these together first because there's a parentheses around those, right? Okay, so now we're going to take the dot product. By definition, the dot product, we're going to take the first component times the first component, then the second component times the second component, and add. All right, so here we go. First component times first component, that's going to be u1 times v1 plus w1. And then the second component times the second component, that'll be u2 times v2 plus w2. And we'll add it together like that. Okay. All right, well, this is just a number times the sum of numbers. I can just distribute this. This has nothing to do with vectors. These are just numbers. So I'm going to use the distributive property of numbers. This is u1 v1 plus u1 w1 plus u2 v2 plus u2 w2. Well, one thing I notice is that these two seem to belong together, right? uv, uv, and uw, uw. Let me rearrange stuff. After all, these are all just numbers. And numbers are commutative. I can rearrange the sum of numbers however I want. So I'll leave that one where it is, and I'll leave this one where it is, u2, w2, but I'll switch the position of those two. So I'll put u2, v2, and then I'll put u1, w1. But then this is the addition of real numbers. It's associative, not just commutative. So I can group it however I like. So u1, v1 plus u2, v2, let me group those two, plus u1, w1 plus u2, w2. Oh, that looks familiar, doesn't it? That's the definition of the dot product. u1, v1, u2, v2. u1, v1, u2, v2. Those are added together. Oh, so that's u dot v. Oh, but that's the same as this, except instead of u1, v1, u2, v2, that's u1, w1, u2, w2. Oh, that must be the dot product of u. Instead of u and v, it'll be u and w. And those are being added together. Oh, but that's what we wanted. U dot, the sum of v and w, is u dot v plus u dot w. And that makes us happy. The proof of all the rest of these works the same way. You're going to go ahead and write out one side in component form. Go ahead and simplify things out, and then separate that back out into vector form, and that should give you the right-hand side. Note that if we wanted to do this in space, you would just have one extra component, u3, v3, w3, and everything would work the same way, except over here you would have had plus u3, v3 plus u3, w3. So that would have just had one extra component here, one extra component here, and you still would get the dot products. All right? So adding the extra component doesn't change how this works. It just gives you one extra component so that you have your third component to have a vector in space. I'll also prove the fifth one, mostly because it's just ever so slightly different than the proof of the first four, and also it's one that we see a lot. So let's go and prove number 5 as well. In fact, I'll actually go ahead and let you try that here. So go ahead and give this a try. By definition, you know what it means to multiply these here. So go ahead and multiply these and see if you can get this side. Go ahead and pause the video. Go ahead and work through that, and once you're done, go ahead and unpause and we can go through it together. All right, so let's take a look. V dot V Okay, well that means I'm going to take, by definition, that's going to be V1 comma V2. And again, I'm going to go ahead and do this in 2 components. If you do it in 3 components, that's fine. It works out the same way. Dot with V1 comma V2. Okay, well by definition, that means you're going to multiply these two together. That's going to be V1 times V1 plus V2 times V2. Okay, but that's a number times itself. You can just write that as V1 squared. And that's a number times itself. You can write that as V2 squared. Oh, but V1 squared plus V2 squared. That almost looks like the magnitude formula, doesn't it? After all, the magnitude formula would be V1 squared plus V2 squared under a square root. Oh yeah, but where are we going to get a square root from? Well, if you put a square root and square it, these are both positive, so taking the square root and the square doesn't change anything. This is equivalent to what we had before. Oh, but now that's the magnitude with a square on it, which is what we wanted. So this confirms our result. The dot product of V with itself is the same as the magnitude squared. As a single quick example of finding a dot product, let's say U is equal to 173, and let's say the vector V is -2, 3, 1. Then the dot product U dot V, which incidentally is okay in either order, V dot U, U dot V, as we see up here, it's all the same, is simply, you're going to multiply the first 2 components, -2 times 1, plus, you're going to multiply the second component, 7 times 3, plus, then you're going to multiply the third component, 3 times 1, and that is, let's see, 21 plus 3 is 24, minus 2 is 22. And there's our dot product. All right, so from this, we see how the dot product is defined, along with some properties that come from that definition. One thing that's not obvious, though, is why is that the definition? Why would you want to call this multiplication? Well, like many things in math, that's our definition because that's the definition that's useful. Let's look at something that gives us a little more intuition as to where this is all coming from. Consider 2 vectors and think about the angle between them. So right now we're going to look at 2 vectors. I'm going to go ahead and draw them on the plane, although the vectors can be in space as well. If you have a vector that's in space and you have another angle that's in space, another vector that's in space, that forms an angle. But even if that angle is up in space, you can always think about it as being on the flat surface here, right? Without changing any of the measurements, you can always take this and flatten it down onto the plane and talk about it as if it were on the plane to begin with. So let's go ahead and consider 2 vectors and the angle between them. So let's say this is the vector u, and let's say this is the vector v. Okay? They have an angle between them. We'll call that angle theta, as is customary. All right. So now let's take the vector v minus u. Okay. Geometrically, what that looks like is, let's go ahead and do this off to the side a bit. If I have the vector u that looks like this, and I have the vector v that looks like this, if I take v minus u, what that means is I'm going to start with the vector v. Let me label that u and v. I'm going to start with the vector v, and then I'm going to subtract u. In other words, I'm going to add a negative u. All right, so if I had v plus u, it would be this u going this way. Oh, but I'm going to subtract u. Okay, so I'm going to go back this way. The opposite. Okay, so from here to here, right, I took my v, and then I subtracted my u. Right? The opposite of that u would be minus u. V minus u gives me this vector here. This is the vector v minus u. Oh, but vectors can be anywhere. As long as they have the same magnitude and the same direction, this vector, v minus u, we could draw it somewhere else. Well, you know what I'm going to do? I'm going to draw it up here. Notice if this slides up this way this point also would slide up this way, and so it would close this off as a triangle. So what that means, if this is the vector u and this is the vector v, then I can close this angle off and form a triangle with this third side, v minus u. So now I have a triangle, which is great because I know trigonometry. I can find the angle between two vectors using the law of cosines. Recall the law of cosines. The law of cosines says if I have an angle, if I have a triangle that looks like this, and I call this A, B, and C, and I call the side lengths little a, little b, and little c, right? Opposite b, opposite a, opposite c. Then the law of cosines tells me that if I take c squared, the side length c, that's equal to a squared plus b squared. It almost looks like the Pythagorean theorem, but then you have minus 2ab times the cosine of the big angle c. Like that. That's the law of cosines from trigonometry. Well, I'm going to do the exact same thing right here with these. All right, so c squared. Okay, well, that one up there is what I'm going to call c, so I just want that squared. Problem is that that's it's supposed to be a side length, right? This is supposed to be the sides of a triangle, 3, 4, 5, or something like that. Here, this is not a number. It's a vector. Oh, yeah, but the number that I want is the length of that vector. Oh, okay, so really, even though this is the vector u, as a triangle, it's a triangle that looks like this. This side length is the magnitude of u. This side length is the magnitude of v. And this top side length is the magnitude of the difference of u and v. And that's the angle theta. So here, that's what we would normally use, right? Here, these are vectors. But trigonometry doesn't use vectors. It just uses a triangle. Okay, fine. Let's look at this triangle, which is really just magnitude, magnitude, magnitude. All right, so let me take the law of cosines on this. C is that one on top. Okay, so that's going to be that magnitude squared. Is equal to, you're going to take this magnitude squared plus that magnitude squared. Minus 2 times the product of the magnitudes, so I'll just call that u and v, times the cosine of the angle c, which over here I'm calling theta. Okay, so here all I've done is I've rewritten the law of cosines using these side lengths and this angle. Just changed a few symbols. All right, so now let's use some algebra to expand this stuff out. Oop, that should be u and v. There's two different sides, yeah? u, v, right? Your a and your b. Okay, so let's go ahead and expand some of this stuff out. After all, I know what these are. This is going to be the magnitude of u is the square root of u1 squared plus u2 squared. That's what we call the magnitude of u. Well, that's being squared. Plus the square root of v1 plus v2 squared. Well, that's the magnitude of v with a square on it. Minus 2 times the square root of u1 squared plus u2 squared. Notice there's no square on that one. And then times the magnitude of v, which is v1 squared plus v2 squared. Again, no square on that one. Times the cosine of theta. So here I've just written all of this stuff based off the definition. And with this one, well, v minus u has components v1 minus u1 and v2 minus u2. So the magnitude would be v1 minus u1 squared plus v2 minus u2, again squared. Oh, but that magnitude has a square on it, just like that. Well, one thing I noticed is that these squares and square roots all cancel out. All the stuff inside is positive, so the square root of the square of a positive is just the radicand inside. So here I'm going to get rid of all those square roots. So that's just v1 minus u1 squared plus v2 minus u2 squared equals u1 squared plus u2 squared plus v1 squared plus v2 squared minus double, now these don't have any squares to get rid of the square roots, so those square roots are going to stay there, times the square root of v1 squared plus v2 squared times the cosine of the angle theta. Okay. Now notice these expand. I can multiply this stuff out. If I multiply this out, that's going to give me v1 squared minus 2u1 v1 plus plus u1 squared. Right? v1 minus v2 times v1 minus v2, you square that out. Plus, do the same thing for this one. v2 minus u2 times v2 minus u2, you distribute, and that'll give you v2 squared minus 2v1 u2v2 minus u2 squared. So that's what I get when I square out the first binomial. When I square out the second binomial, I get all of these. So that's v2 squared minus 2u2v2 minus u2 squared. And over here I haven't done anything, so I'm going to rewrite that as u1 squared plus u2 squared plus v1 squared plus v2 squared minus 2 square root of u1 squared plus u2 squared times the square root of v1 squared plus v2 squared times the cosine of the angle theta. Now this might look absolutely horrifying until you realize almost everything cancels out. Hey, look, u1 squared is on both sides of my equation. So if I subtract u1 squared from both sides, that just becomes 0. That should be a plus, right? When I square negative u squared, negative 2u times negative 2u is positive u2 squared. Why didn't anybody tell me? Those two are the same. So if I subtract u2 squared from both sides of my equal sign, that goes away. Likewise, v1 squared and v1 squared is on both sides of my equal sign. So that one, if I subtract it from both sides, that's gone. And v2 squared and v2 squared is the same. So if I subtract that from both sides, that's all gone. So now I'm left with something much, much simpler. I'm left with negative 2u1 v1 minus 2u v2. Everything else is gone. Those 4 terms are gone. Just leaves me those 2. Equals. All 4 of those are gone. And I'm just left with this. Minus 2 times the square root of u1 squared plus u2 squared times the square root of v1 squared plus v2 squared times the cosine of the angle theta. Notice these are all these all have a common factor of negative 2. So what I can do is I can divide everything by negative 2. And if I divide those by negative 2, that is now a positive 1. And that's also a positive 1. And that's a positive 1. So I'm left with u1 v1, plus, double negative makes a plus 2, I've divided my 2's away. So that's just plus u2 v2. And that's equal to, these have divided away, and that's the square root of u1 squared plus u2 squared times the square root of v1 squared plus v2 squared times the cosine of theta. All right, well, what I'm looking for is the angle theta. So I can divide these away, and what I'm left with is the cosine of theta equals u1 v1 plus u2 v2 divided by the square root of u1 squared plus v1 squared times, that should be u1 squared plus u2 squared times the square root of v1 squared plus v2 squared. But we know what these are. These are just the magnitudes of u and v. So here that's equal to u1 v1 plus u2 v2 over the magnitude of u times the magnitude of v. Whenever people were looking for an angle, whenever people started with vectors, when all this stuff was originally being studied, and when people started doing computations and trying to figure out, okay, given vectors, how do I find the angle between them? This term kept appearing. or rather these terms kept appearing. U1v1 plus U2v2. Since those kept appearing in several instances, in fact, in lots of things that we'll see throughout this course as well, if it is important enough to appear over and over again, it's probably important enough to have its own symbol. So we give this its own symbol, and we call it the dot product. That's why our definition, U1v1 plus U2v2, U1v1 plus U2v2, because that kept appearing everywhere, well, then we may as well give that a name. So we call that the dot product. So this is U dot V over the magnitudes of U and V multiplied together. So this shows us two things. One, it shows us why this is a way we want to define multiplication, why it's a way we want to define something that involves vectors, because it's something that appears commonly in a very common type of computation. Not just when we're talking about angles, but when we're talking about lots of other things, as we'll see throughout this course. But not only does it show us why this is what we want to define as multiplication, or at least one of the things that we want to define as multiplication, it also shows us how to find the angle between two vectors. So here, theorem. I've gone ahead and done this in reverse. Usually I would give you a theorem and then a proof, but here it seems I've done it backwards. This is the proof. The proof of what? Well, the proof of the theorem that we're about to state. We say let theta be the angle. Now, whenever you have two vectors, you have two angles you can talk about. You can talk about the smaller angle, or you can talk about the larger angle. We're always going to talk about the smaller angle. So let theta be the, I'm going to put here smaller. That's not actually part of the theorem, but sometimes it throws people off to say, well, wait a minute, what about the other one? Here, we mean the smaller of the two. Let theta be the smaller angle between two non-zero vectors. We don't want them to be zero, because if they're zero vectors, then these denominators are zero, and then the whole thing is undefined anyway. So here we want theta to be the smaller angle between two non-zero vectors. Which we'll call U and V. Then the cosine of that angle theta must equal to the dot product of the two vectors divided by the product of the magnitudes of the two vectors. This allows us to compute the angle theta. And here, proof see above. That's the proof. So as an example, let's go and find the vector between the following two angles. Let's find the angles between the vectors u, which is given by 3, let's see here. This is given by 3i plus 4j, and the vector v, which is given by negative 2j plus 3k. Okay, this is sometimes a little confusing. This might throw people off. Right here, this is a vector in 3 dimensions. It just so happens that the third component is 0 here, and the first component is 0 here. So you may wish to actually fill that in. You may wish to say, okay, that's 0k, and that's 0i. Or you may even wish to write it this way, where we have 3, 4, 0, and where we have 0, minus 2, 3. in any event, we do need those zeros there. Okay? So the cosine of the angle theta is going to be the dot product of u with v over the magnitude of u times the magnitude of v. Like that. All right, so it looks like we're going to need these magnitudes. So let's find what those are. The magnitude of u, that's going to be the square root of the sums of the squares of the components of u, which are 3, 4, and 0. All right, well, that's 9, 16, and 0. So that's going to equal to root 25, which is just the number 5. The magnitude of v is going to be the square root of the sums of the squares of, let's see, 0, -2, and 3. Which is, let's see, that's 0, 4, and 9. So that'll be root 13, which doesn't simplify nicely. So that's going to be my denominator. It's going to be 5 root 13. And then in my numerator, I need the dot product of u with v, which is, component-wise, 3 times 0 plus 4 times -2 plus 0 times 3, which is 0, plus -8 plus 0, which is -8. So that is the cosine of our angle, which means that our angle is equal to the inverse cosine, or the arc cosine, depending on your preferred language, the inverse cosine or the arc cosine of -8 over 5 root 13. That's a perfectly good answer, but if you insist on having a decimal approximation, of course you can always pull out one of these clunky looking things, yes? All right, so let's see. I have my calculator set in radians. Just about everything in this book, it's usually okay if we leave it in the exact form, but if you're gonna approximate it, just about everything's done in radians. It's rare that we see degrees. So unless you're told otherwise, assume that everything's in radians. So -8 divided by the product of 5 times root 13. And then we're going to take the arc cosine of that, and that'll give us that many radians, 2.0306. Whenever we're dealing with decimal approximations, we'll round off to 4 decimal places. Why 4? Honestly, just something I've gotten used to over the years. Most of our textbooks that we use, both when I was a student as an instructor, for some reason 4 decimal places seems to be the magic number that's used in almost every book that I've ever seen. So here, I'm going to go with that apparent convention, 2.0306. Since it's in radians, radians is a unitless measure. So if I want to, I can write radians, or I can just say that, and without any measure, it's assumed that we're talking about radians. And there we go. So the measure is that. Of course, if you prefer it in degrees, I suppose you can do that as well. But just keep in mind that most of the things that we do will be done in radians, because radians are a unitless measure, and if you're dealing with degrees, you may often have to convert anyway. So that's our result. One thing to note, if the dot product of u and v is equal to 0, then the cosine of the angle between those two vectors is equal to 0 over the magnitude of u times the magnitude of v, but doesn't matter what this is, 0 divided by anything is still 0. So the cosine of theta is equal to 0, which suggests that theta must equal to pi over 2, or if you prefer degrees, 90 degrees. Okay, so 90 degrees for pi over 2, if we're thinking geometrically, that's those two lines are perpendicular to each other. Well, okay, but that happens anytime your dot product is equal to 0. So we have a name for that. Definition. Let u and v be vectors And it doesn't matter if they're in the plane or in space, as long as they're vectors, right? Let U and V be vectors. If the dot product of U and V is equal to 0, then that means that the angle between them will be pi over 2, will be 90 degrees. We say that they are orthogonal. U and V are orthogonal. Geometrically, you can think of that as being they're at a 90-degree angle. The reason we have another word for it, aside from, well, there's just another word for it, is orthogonality has more to do than just geometry. Parallel just means, oh, these two things meet at 90 degrees. As you go into higher levels of math, you'll start to encounter other situations where, oh, these functions are orthogonal. Oh, these matrices are orthogonal. What does that even mean? How do you have two functions meet at a 90-degree angle? That doesn't, I'm not quite sure what that means. So eventually it comes to the point where the word perpendicular, although is, I suppose, technically correct, becomes confusing because perpendicular has a geometric interpretation. So instead we use the word orthogonal to denote something similar, but with less of a connotation of being geometric. So here, yeah, when it comes to two vectors, you can think of them as they're crossing at a 90-degree angle. When it comes to functions, well, we talk about that in later courses. Yeah? So here, if you have the dot product, those vectors are called orthogonal vectors. Another thing to note, we know that the cosine of the angle theta is equal to U dot V over the magnitude of U times the magnitude of V. If I multiply this over to the other side, this tells me that U dot V is equal to, well, this is multiplied over here. That's now going to be U magnitude of U times magnitude of V times the cosine of the angle theta. This is another way of defining the dot product. The dot product of two vectors is the product of their magnitudes times the cosine of the angle in between them. This is not anything different than what we just saw. It's identically this statement. However, by looking at it in the context of solving for the numerator, this is regarded as an alternate definition, a more geometric definition rather than the algebraic one that we have from before. We define the dot product algebraically over here. This is more of a geometric one. What does it mean to have a dot product? Oh, it means take the lengths of the vectors and then multiply by the angle in between them. This is often regarded as an alternate definition, a more geometric definition of the dot product. We will occasionally use this definition to prove some things. So for now, we just make a note of it. We can use this concept of finding the angle between two vectors to give us some reference angles to some arbitrary vector in space. What does that mean? All right, consider the x, y, z coordinate system, the right-handed XYZ coordinate system. In other words, space, not the plane. All right, well, we've seen the right-hand rule, so we'll call this one X. All right, we'll call that X, and then Y. And then my thumb is pointed in the direction of Z. Right? So X, Y, Z. X, Y, and Z. Okay. Now let's say I have a vector pointing in some arbitrary direction, something over here. Here's my vector. All right, well, how do I define that? Well, how do I define a vector in the plane? All right, well, let's see. When I have a vector in the plane, that's a lot simpler because all I have to do is I define it by its magnitude times its angle, or well, times the sine and cosine of its angle. Well, what angle? What do you mean by its angle? Oh, well, we have a way of measuring angles in the plane, right? We have starting from the positive half of the x-axis, we can just measure this angle, which we'll call theta. Well, then why don't I do that over here? Why don't I just measure the angle from the positive half of the x-axis? Well, because that's not going to really work for me, is it? Because after all, this vector right here, if I measured this angle from the positive half of the x-axis, well, that's nice and all, but if I shift this vector and point it straight down this way, just like instead of pointing up, I would just have it come straight down, then wouldn't that have the same angle there? Yeah. In fact, because there's so many degrees of movement here, I could swing this around this way and it would also have the same angle. So just saying I want the angle from the x-axis to the vector isn't really going to work for me. Well, okay, but what if I had more vectors? What if I had the angle between the x-axis and here, between the y-axis and here, and between the z-axis and here? If I had all three of them, then that's got to be the only vector that has all three of them, because if I swing it in any direction, it's going to change at least one of them. Well, yeah, but that doesn't make any sense to have the angle between the axis and this vector. That's not how we define angles in space. We define the angle between one vector and another. Okay, so we can't just use the axis. I have to use a vector on the axis. Oh, well, that's the vector I. And that's the vector j. And that's the vector k. So if I can find the angle from the vector I to my vector v, I'll call that alpha. And again, that's the shortest angle, alpha. And if I find the vector, if I find the angle from the vector j to the vector v, I'll call that one beta. So, and then if I find the shortest angle between my vector k and my vector v, I'll call that gamma, alpha, beta, and gamma. Then these three angles together serve the same way this angle did on the plane. They help me figure out what direction I have. So instead of referencing a direction with just one angle, here I'm forced to improvise. I can find the angle. I can find the direction based off of three different angles. It's tethered to three different lines which hold it in place. Okay, so how do I do that? Well, let's see here. I'm going to use, as I mentioned, we can use this. I'm going to use my alternate definition of the dot product. I'm going to find the dot product between my vector and I. Okay, so let's see here. The vector v dot I. Okay, the reason I'm using this is because this shows me something about the cosine of the angle. And that's what I want. I want to figure out this angle. So v dot I, okay, that's going to equal to the magnitude of v times the magnitude of I, times the cosine of the angle between v and I, which, again, I don't want to call theta here. The angle between v and I, I'm calling that alpha. Okay. Now, one thing to note is that the magnitude of I is equal to 1. After all, it is a unit vector in the direction of the x-axis. So here, this is just the number 1. So I don't even have to worry about that. V dot I is equal to the magnitude of v times the cosine of the angle alpha. Okay, but I also have that the vector v dotted with the vector I, well, by definition, that's v1, v2, v3. After all, that's a vector in 3 space, dotted with the vector I, which is one step in the x direction, and then it doesn't have any steps in the y or the z direction. So 0, 0, which is really just v1 times 1 plus v2 times 0 plus v3 times 0. Which, that's just v1. The rest are 0. Okay, so v dot I is equal to this, but v dot I is also equal to this. Okay, so by the transitive property, so that means that that must equal to this. Okay, so v1 is equal to the magnitude of v times the cosine of alpha. This one's equal to that one. And if I divide both sides by the magnitude of v, that tells me that the cosine of my angle alpha is equal to V1 over the magnitude of V. And there we go. That helps me find that angle alpha. Doing the exact same argument, but instead of having with I can do V dot J or V dot K to find beta and gamma. I find the exact same results. So this gives us the direction angles. We find that given a vector V, in space, okay? And let alpha, beta, and gamma be the angles between V and I, J, K, respectively, meaning alpha is V and I, beta is B and J, and gamma is V and K, so respectively in order. Then we find that the cosine of alpha is equal to V1 over the magnitude of V. We find that the cosine of beta is equal to V2 over the magnitude of V. And we find that the cosine of gamma is equal to V3 over the magnitude of V. Here, alpha, beta, and gamma define the direction angles of V. Definition. Are the direction angles of V. One thing to note, this, and this, these look familiar? These are the components of the unit vector in the direction of V. Recall, U, which is equal to V1 over magnitude of V, comma V2 over magnitude of V, comma V3 over magnitude of V, is the unit vector. How did I misspell the word unit? Is the unit vector in the direction of V, in the direction of U. No, in the direction of V. Oh, but each individual component is the cosine of those direction angles. So another way to define U, the unit normal vector, unit normal vector. That word will come up later. Normal means something in relation to space here. The unit vector in the direction of V can also be written, now here these are the same U, can also be written as cosine of alpha, comma, cosine of beta, comma, cosine of gamma. It also follows that because these are the components of a unit vector, then the magnitude of this vector must be 1, which means that, well, how do you find magnitude? You take each of the components, square it, and add them together. Cosine of alpha squared plus cosine of beta squared plus cosine of gamma squared under a square root, right? That's the magnitude of U. That's got to equal to 1. But I can take the square of both sides. Square of 1 is still 1. And here, since these are all positive, I just get rid of my square root without having to worry about my sign. So you get that the cosine squared of alpha plus the cosine squared of beta plus the cosine squared of gamma must equal to 1. So here's a relationship between all three of the angles, the direction angles of V, and it comes directly from the fact that these direction vectors are the components of the unit vector in the direction of V. So you give me a vector in space. I can scale it down so that it's a unit vector. Down here, a unit vector in the same direction, but it's only 1 unit long. The components of that are going to give you the cosine of alpha, beta, and gamma, which is nice. So for example, find the direction angles. Of the vector -4, 3, 5. Go ahead and give that a try. Basically, you're normalizing this. You're making it making this into a unit vector. And then once you have that, that's going to give you the components necessary to find your unit vectors, alpha, beta, and gamma. So go ahead and give that a try. Pause the video and see what you get. And once you're done, go ahead and unpause and we'll go through it together. All right, so let's take a look. First of all, if that's the vector V, I'm going to label that. Let's call that V. Then what I want to do is I want to find the magnitude of V. All right, well, I know the magnitude of a vector is the square root of the sum of the squares of the components. And those components are -4, 3, and 5. All right, so that's going to be the square root of 16 plus 9 plus 25, and that's the square root of 50. Which is what? 5 root 2. Right? The square root of 50 is 25 times 2, like that. Square root of 25 times 2. And I know the square root of 25, that's 5. And I just use my root 2 inside. All right, so there we go. There's my vector. There's my vector's magnitude. So now I can find the unit vector in the direction of V, which is just take your V and divide by the magnitude of V, which means I'm just going to take all of these and divide by 5 root 2. Okay. All right, so there is my unit vector in the direction of V. Normally I'd go through and rationalize these, but I'm not really done yet. I don't really worry about simplifying and rationalizing till the last step, right? So here, this is my unit vector in the direction of V. But notice that those components are exactly what I need to find cosine of alpha, cosine beta, cosine gamma. So here that's going to give me that the cosine of alpha is equal to -4 over 5 root 2. I get that the cosine of beta is equal to 3 over 5 root 2. And I get that the cosine of gamma is equal to 5 over 5 root 2. I can just divide the 5's away. That's 1 over root 2. Incidentally, these also have a name. These are called the direction cosines. So if you don't solve for the angles, you just leave cosine of alpha, cosine beta, cosine gamma. These are called the direction cosines, which I never liked the name of, but that's what they're called, the direction cosines. Here, to find the direction angles, you simply take the arc cosine of both sides, or the inverse cosine if you prefer that language. They mean the same thing. Well, that one is one that we know off the top of our heads, right? Think back to trigonometry. That's what, pi over 4? It's pi over 4. If you, here, I don't know these off the top of my head. So here we could go through and try to find some more precise values. But here, I think we'll just grab one of these things, yeah? Let's see here, -4 over 5 times root 2 Okay, so I'm going to take the inverse cosine of that, and that'll give me approximately 2.1721. And that's in radians. If you prefer degrees, all right, whatever. But for the most part, we're going to do with radians in this class. 3 divided by 5 times root 2 is equal to that. Then I can take the inverse cosine of that, and that'll give us 1.1326. And then here the inverse cosine of 1 over root 2, that's pi over 4. So here I'll just pi over 4. Right? Pi divided by 4. That's if I'm doing these as a decimal, I might as well do that one as a decimal. 0.7854. And here, if you didn't remember that one, then we just take 1 divided by the square root of 2 and take the arc cosine, and well, same thing, either way. So there we go. These are our direction angles. These are the angles between, to find the vector v, starting from I, you would traverse this angle. From the vector j, you would traverse this angle, and from the vector k, you would traverse this angle. And that gives us our direction angles. So this brings us to another definition. So let's start off with a couple of non-zero vectors. Let u and b be non-zero vectors. Okay. Now, let the vector u be composed of the sum of two other vectors. We're going to call those vectors w1 and w2. Okay. Here, these two vectors are not just arbitrary vectors. They are vectors which, the first one, we're going to say is parallel to the vector v, and the second one is perpendicular, is orthogonal to the vector v. Okay. Remember the definition of orthogonal, if the dot product of these two is 0. Okay. Before we proceed to finish defining this, let's go ahead and illustrate what we have. Let's say we have a vector u and a vector v, and these are just arbitrary non-zero vectors. Any vector is fine as long as it's not a zero vector. So I'll call this one u, and I'll go ahead and call this one v. And v doesn't have to be horizontal like this. It's just, for the sake of illustration, it's easier for me if I just draw it this way. All right, now, this vector u is going to be such that it's made up of the sum of two other vectors. But those aren't going to be just two random vectors. One of those vectors has to be parallel to v. So it has to run alongside v, just like this. Right here, so this one right here would be w1. And then w2 would be orthogonal, perpendicular to vector v. So like this. Right? So right here, u is made up of these two, where one of them is running alongside v, and the other one is coming straight out of v, perpendicular. Okay? In that case, w1 is what's called the projection of u onto v. And it's denoted w1 equals the projection, P-R-O-J, of u onto v. The subscript one is the one you're projecting onto. U is the one that's doing the projecting. Like this. So W1 is the projection of U onto V. Meanwhile, W2 also has a name. W2, which is really just U minus W1, this one that's left over. This is called the vector component of U orthogonal to V. We don't use this one too often. The projection is the one that we're most interested in for most applications in this course. However, these two are defined at the same time, so we do put them together. Okay. Here, one way to visualize this, think of it as a shadow. Imagine V is the ground, and this is like a tree. All right, so here we have the ground, and we have a little palm tree. There we go. Palm trees have coconuts. There we go. There's coconuts. All right. So now it's a bright sunny day. Here's the sun. There we go. All right. So the sun, this object is not on the ground. However, it will project a shadow. That shadow is the projection. This is the projection of the tree onto the ground. The projection of U onto V. So the V is acting like the ground, and the U is acting like the tree whose shadow is being cast. The projection is that shadow. Not a perfect parallel to the, pardon the pun, it's not a perfect parallel to the image, but it does help give a little more of a solid feel to this. All right, so that is our definition. Okay, so how do we find one of these projections? So that brings us to a theorem. Let's say you have two vectors, non-zero of course, otherwise a lot of this stuff doesn't work. Let U and V be, actually let me go ahead and write that, be non-zero vectors. Then the projection of U onto V, remember the notation, the way this works, U is the one you're projecting, V is the one you're projecting onto, U is your tree, V is your ground. The projection of U onto V is given by U dot V over the magnitude of V squared. Notice the dot product is a scalar. The magnitude is a scalar. Squaring a scalar still gives you a scalar. And a scalar divided by a scalar, that's a scalar. This is just a number. Number 5, number 12, whatever the number is. That's going to get multiplied by the vector V. So it's a scalar times a vector. Just like that. This may seem a little intimidating, but the proof of this is almost entirely trigonometry. There's very little in terms of what we have here. And here you may even recognize U dot V over the magnitude of U times the magnitude of V. That would just be the cosine of the angle theta between the two vectors. Right? So that's not exactly the same, but it looks very similar to it. So I would imagine that's involved, yes? So let's talk about the proof of this. You might want to try this one. You might want to pause the video and give this a try if you, especially if you're planning to continue on to other math classes after this. Being familiar with proving things is a useful skill to have. Go ahead and pause and come back and confirm it together. All right, so the proof of this is really very geometric. Use a little trigonometry. Consider two vectors. And again, they don't have to be where one's horizontal, but I'm going to draw it that way because it's easier for me to draw. You say, well, what if one was not horizontal? What if it was like this? Well, then rotate it till it's horizontal. Simple enough. Okay, so here's the vector u, and here's the vector v. All right, so what we're looking for is we're looking for this vector right here. This is the goal. Okay. Now remember, there is a second vector here that is perpendicular to the vector v, and when you add those two together, you get the vector u. All right, well, this is a 90-degree angle. These are parallel, these are perpendicular, which must mean this is 90 degrees. Okay, so if that's 90 degrees, well, then we have trigonometry on our side. Let's call this the angle theta. Okay, well, this is the vector u. Oh, I should draw it with a little arrow, right? And there goes a vector. All right, so this, if I take the side lengths, that's a triangle, right? So if I have this, that's the side length. Okay, well, the magnitude of u would be that side length. And then I have this side length, and I have this side length. And here's an angle. All right, well, let's see. This right here is my projection. Well, it's not. My projection is supposed to be a vector. This is just the length of a side. Oh, okay, well, then that's the magnitude of my projection. Oh, well, that's just cosine, right? Adjacent over hypotenuse. The cosine of the angle theta is equal to the adjacent side, which is the magnitude of my projection, over my hypotenuse, which is the magnitude of u. Like that. So right here, I could just go ahead and multiply this over to the other side, and I could get that the magnitude of the projection that I want, the magnitude of the projection of u onto v, is equal to the magnitude of u times the cosine of the angle theta. Oh yeah, but I know the cosine of the angle theta, that's given to me by a dot product, right? Here, that's equal to the magnitude of the vector u times the cosine of the angle theta is given by the dot product of u with v. Ooh, that's where that dot product's going to come from, isn't it? Divided by the magnitude of u times the magnitude of v. Oh, look, these are common. They divide away. After all, they're just numbers. So that means that the projection of u onto v has a magnitude that's given by u dot v over the magnitude of v. Oh yeah, but that's just the projection. Sorry, that's just the magnitude of the projection. I didn't want the magnitude. I want the full projection. Oh, well, I know how long it is. Now I just need to know what direction it's going in. Well, that's easy. It's going in the direction of v. Okay, so I need a vector that's in the direction of v, but that has this magnitude. Well, I don't know how to find a projection of, I don't know how to find a vector that's parallel to v that has that projection magnitude, but I do know how to find a unit vector in the direction of v. Note that I can take v divided by the magnitude of v. And that's going to be the unit vector in the direction of v. Over here, this is the magnitude of the projection So if I put these together, hey, here's my vector. Oh, but it's the wrong size. This is a unit vector. I need to scale it so that it's the right size. Oh, well, then I take this one and I scale it by this amount because this tells me how long it's supposed to be. This has magnitude 1. So 1 times this, oh, it'll give me a magnitude that's this. So that means that my projection of u onto v must equal to, that's in the right direction, but it's only got magnitude 1. But by multiplying it by this magnitude, But by multiplying it by this magnitude, u dot v over the magnitude of v, that gives me this vector with the right size. Here, these two are the same, so I can say, well, the magnitude of v times the magnitude of v, I can write that as the magnitude of v squared. And then that's just the vector v, which is exactly what we were supposed to get. So here, to compute the projection of u onto v, you take the dot product of u with v, divide by the square of the magnitude of v, and then multiply the whole thing by the vector v. So let's take a look at an example. Let's go ahead and find the projection of. Note that we never really said what these vectors have to be in, whether they have to be in the plane or in space. It actually works regardless of dimension, as long as these two are in the same dimension, as long as they're both on the plane or they're both in space. So here, you can define the dot product for the plane or for space. Same thing, you can define the magnitude of a vector for the plane or space. So it doesn't really matter what you happen to be in. All right, so let's go ahead and give this a try here. Let's let u be given by the vector negative 9i minus 2j minus 4k. And let's let the vector v be given by 4j plus 4k. Once again, these are clearly in three dimensions, I, j, and k. This one's missing its first term here, so let's go ahead and write that as 0i, just to keep us from losing a value. If you prefer, for example, I prefer to have things in component form, so you may wish to write things this way. And if you're fine leaving it that way, or if you prefer leaving things that way, or if you prefer writing things that way, go ahead. They're identical. They mean all the same. All right, so here's u and v. So now the question is, find the projection of u onto v. All right, well, simple enough. We're following this. U dot v over magnitude of v squared times v. Okay? So this will be a fairly straightforward application of the result of that theorem. So go ahead and give that a try. Pause the video, take a couple of minutes, and once you're done, go ahead and unpause and we'll confirm the answer together. All right, so we're going to take the dot product of u and v. Let me go ahead and do that up here. If I take the dot product of u and v, that's going to be, well, just multiply component-wise and then add those results. That would be negative 9 times 0 plus negative 2 times 4 plus negative 4 times 4, which will give us 0 minus 8 minus 16, or in other words, negative 24. All right, so that's our numerator, negative 24. Let's go ahead and find the magnitude of the vector v. That's going to be the square root of, now this has three components, so that's going to be v1 squared plus v2 squared plus v3 squared. Like that, v1 squared, v2 squared, v3 squared. Oh, but we want the square of that magnitude. Okay, so let's square both sides here. And that gets rid of that square root. So really it's just v1 squared plus v2 squared plus v3 squared. Okay, well, we can have all those values. That's going to be v1 squared plus, we're going to take v2 squared, and then v3 also squared. And we're going to add all those together, which will give us 0 plus 16 plus another 16, which is 32. And finally, we're going to take that scalar, we're going to multiply it by the vector v, which is 0, 4, 4. Note that does reduce 24 over 32. We can divide everything by, is that 4? No, 8. We can divide everything by 8. So here that'll give us negative 3 over 4 times 0, 4, 4. So in the end, our projection would be, anything times 0 stays 0. Negative 3/4 times 4 is just negative 3. And negative 3/4 times 4 is, again, negative 3. Oops. Beating up my camera. So here, that is the projection of u onto v. Note these are not commutative. If you switch these, if you say the projection of v onto u, it will not give you the same thing. All right, so here, note that the one that's being projected only appears once right here. The one that you're projecting onto appears everywhere else, there, there, and there. And that's it for this section. If anybody has any questions, comments, or problems, please make a note of those and reach out and let me know, and I'll help you as best I can. I hope everyone has a nice day.